In the realm of wearable-based human activity recognition, the authors propose a novel approach that leverages vector quantization, (VQ), to learn discrete representations of movement data without annotations. This self-supervised method involves convolutional blocks for encoding sensor data, followed by a vector quantization module that replaces the encoding with the nearest codebook vector. A causal convolutional encoder is then employed to predict future time steps of data in a contrastive learning setup. The authors demonstrate the efficacy of their discrete representation learning using wrist-based accelerometer data from the Capture 24 dataset, contrasting their approach against other representations, including end-to-end training and self-supervised learning. The evaluation is performed on 6 diverse benchmarks, showcasing the potential of discrete representations for various activities. This research paper presents a novel approach to learning discrete representations of human movements using wearables-based sensors, combining learned VQ with self-supervised learning methods. The paper discusses various computational methods for discretizing sensor data, including symbolic aggregate approximation, SAX, multivariate bag of SFA symbols, emboss, and word extraction for time series classification, WEASL. The proposed method utilizes the vector quantized variational autoencoder, VQVAE, to generate discrete codes instead of continuous latents, allowing for a differentiable mapping of data to a codebook of vectors. This enables modeling long-term dependencies through the compressed discrete latent space. The paper highlights the potential impact of learned discrete representations beyond standard activity recognition, including activity discovery, activity summarization, and fingerprinting for large-scale behavior assessments. The authors draw parallels with speech recognition, where discrete representations have shown great promise, enabling a differentiable mapping of spans of audio waveforms to a codebook. Techniques like VQ-Wave2-Vec and Wave2-Vec 2.0 represent the state-of-the-art in speech recognition, with the introduction of extensions including the use of Roberta pre-training and acoustic models for improved speech recognition. The paper concludes by discussing the potential of the new learned discrete representations for various applications and future work. This research paper introduces a novel framework for learning discrete representations of human movements from wearable sensor data, leveraging self-supervised learning paradigms and vector quantization. The proposed method combines a contrastive future time step prediction problem with vector quantization, utilizing the Enhanced Contrastive Predictive Coding (CPC) framework to capture slowly varying features in the sensor data beneficial for representation learning. The framework consists of a convolutional encoder that maps windows of sensor data to latent representations, and an aggregator that summarizes previous latent representations into a context vector. The encoder comprises 4 blocks with 1D convolutional networks, ReLU activation, and dropout, resulting in a reduction of temporal resolution. The aggregator is a causal convolutional network that enables improved parallelization and faster training times. Vector quantization is applied to the latent representations, where each representation is replaced with the index of the closest codebook vector. The codebook consists of V representations of size D, and the nearest neighbor codebook vector to any latent representation is chosen based on Euclidean distance. This process can be considered a nonlinearity that maps latent representations to one of the codebook vectors. The online commens-based quantization is used, which is similar to the vector quantized autoencoder. The quantization module replaces each latent representation with the index of the closest codebook vector, and the aggregator summarizes previous quantized representations into context vectors used for predicting multiple future time steps. The architecture can be adjusted to accommodate different sampling rates, and the output frequency of the encoder can be modified by changing the convolutional encoder architecture. The proposed framework substantially improves the performance of the learned representations compared to state-of-the-art methods, enhancing human activity recognition and providing a deeper analysis of human movements. In this research study, the authors introduce a novel approach for learning discrete representations from sensor data using self-supervision. They propose an architecture that consists of an encoder, a quantizer, and a decoder, with the quantizer mapping the output of the encoder to a discrete representation by selecting the closest codebook vector. This discrete representation is then used as input to a classifier network for activity recognition. The authors also discuss the importance of preventing mode collapse, where only a few codebook vectors are utilized, and propose independent quantization of partitions to mitigate this issue. The study utilizes 5 datasets: Capture 24, HHAR, Myogem, Mobiact, MotionSense, and mHealth, which vary in terms of sensor locations, number of users, and activities performed. For data preprocessing, a single accelerometer is used for both pre-training and evaluation. The sampling rate of Capture 24 is reduced to 50 Hz, and all target datasets are downsampled to 50 Hz. The window size is set to 2 seconds with an overlap of 0 for Capture 24 and 50% for target datasets. The dataset is split randomly by participants at a 90:10 ratio for training and validation. For evaluation, the target datasets are separated into 5 folds, with the first fold split at a 80:20 ratio by participant into trainable and test sets. The remaining folds are constructed by randomly choosing 20% of the participants as the test set, ensuring no participant appears in more than one test set. The implementation details of the study utilize the PyTorch framework. For self-supervised baselines, the performance is reported as detailed in the original enhanced CPC paper. The discrete version of CPC is implemented with a learning rate in L2 regularization set to 1E4, and the loss weighting parameter is set to 0.25. The prediction horizon is set to k equals 10 with the number of negatives equal to 10. Early stopping with a patience of 5 epochs is employed, and a cosine learning rate schedule is used. This research paper focuses on learning discrete representations of human movements for wearable-based human activity recognition. It evaluates the effectiveness of these representations using a GRU classifier and compares their performance against established supervised and self-supervised baselines. The study explores the impact of controlling the resulting alphabet size and the effect of sensor data duration on the representations. Additionally, it applies self-supervised pre-training techniques designed for discrete sequences to improve recognition performance. The results show that discrete representations perform comparably or better than self-supervised and supervised baselines on 3 of the benchmark datasets, indicating the capabilities of the learned symbols. However, performance varies significantly across different activities and sensor locations, with discrete representations excelling in locomotion-style activities but struggling with fine-grained gym activities. The paper also discusses the use of discrete representation learning for wearable-based human activity recognition, comparing the performance of the proposed technique, VQCPC, with established methods like SAX and SAXREPEAT. VQCPC outperforms both SAX and SAXREPEAT on various datasets, including HHAR, Myogem, Mobiact, MotionSense, mHealth, and PAMAP2. This is attributed to the ability of VQCPC to learn a better mapping of sensor data to discrete representations. The study also investigates the impact of the maximum dictionary size on activity recognition, finding that limiting the size to 64 or 128 can result in significant performance improvements. The optimal dictionary size depends on the required fidelity and computational power. Overall, the research highlights the effectiveness of discrete representation learning for activity recognition and its potential to improve performance and reduce data upload costs. This research explores the impact of varying the output frequency of a convolutional encoder on the performance of human activity recognition in wearable-based systems. The study observes that an output frequency of 24.5 Hz results in better performance while reducing computational costs. Additionally, the use of pre-trained Roberta embeddings for classifying discrete representations improves activity recognition performance, achieving state-of-the-art results for 3 datasets. The authors also investigate the use of self-supervision to learn discrete representations, utilizing small and medium Roberta models. The results show that using learned Roberta embeddings leads to performance improvements across 5 target datasets. The distributions of the discrete representations exhibit long-tailed distributions, with significant portions being used very sparsely, which may increase the complexity of classifiers and embeddings. Overall, the study demonstrates the effectiveness of using self-supervision to learn discrete representations for wearables-based human activity recognition and the potential for applying advancements from natural language processing to improve activity recognition. This research paper presents a novel approach to learning discrete representations for human activity recognition using self-supervision. The study explores the impact of the encoder network architecture and the base self-supervised method on recognition performance, concluding that a filter size of 4 in the encoder network is ideal and the enhanced CPC self-supervised method offers the most suitable framework for discrete representation learning. The proposed method demonstrates that the performance of activity recognition systems based on learned discretized representations is comparable to, if not better than, when using dense, continuous representations derived through state-of-the-art representation learning methods. This approach has significant implications beyond standard activity recognition, including leveraging established methods from natural language processing to extract key information or summarize the most informative sensor data. It also allows for a better understanding of routines and reduces noise in the data. Moreover, the paper discusses the potential for activity and routine discovery, where typical healthy behavior can be characterized by such discovery algorithms, and discovering motifs is easier in the discrete space. The method is highly effective for recognizing locomotion and daily living style activities at the wrist and waist, resulting in the best or similar to the best performance for 3 benchmark datasets. However, the loss in resolution due to the mapping to a small set of discrete symbols negatively impacts scenarios where the fine-grained activities need to be recognized. Therefore, potential future work could include exploring Gumbel's softmax vector quantization and additional losses that can promote diverse codebook usage, aiding more fine-grained movements to be represented by their own symbolic representations, resulting in improved recognition. The research focuses on developing a novel approach for wearable-based human activity recognition by casting the multi-channel time series classification problem as a discrete sequence analysis problem, similar to natural language processing. This involves the use of powerful NLP-based pre-training techniques, such as RoBERTa, to improve activity recognition for various target datasets. The study demonstrates the effectiveness of this approach by achieving better representations through explicit control of the maximum dictionary size. The methodology leverages self-supervision, utilizing techniques like masked reconstruction and contrastive predictive coding to learn discrete representations. The results show significant improvements in activity recognition, highlighting the potential of this approach for real-world applications. The research also discusses limitations and future work, emphasizing the need for further exploration into the integration of other modalities and the development of more robust evaluation metrics. Here is a combined summary of pages 29 to 30. The supplementary visualizations and mathematical formulations presented in this section provide further insight into the self-supervised learning approach for wearables-based human activity recognition. Figure 7 displays the histograms of discrete representations per class for the first fold of the MotionSense dataset, showcasing the full range of symbols and extending Figure 6, which truncates the z-axis to 50 symbols. This visualization highlights the diversity of symbols in each class, essential for effective human activity recognition. Figure 8 illustrates the weight updates of the VQ-CPC architecture, a critical component of the proposed self-supervised learning framework. The aggregator network is updated using the sum of contrastive predictive coding losses, denoted as n-ary summation k equals 1 KLCPCK. The codebook vectors are updated based on the Euclidean distance between the stop gradient vector SG, Z, and the quantized vector Z, represented as parallel SG, Z, minus Z parallel 2. The encoder is updated using a combination of both the contrastive predictive coding losses and the commitment loss, which is proportional to the Euclidean distance between the original vector Z and the stop gradient vector SG, Z, denoted as gamma parallel Z minus SG, Z, parallel 2. These visualizations and mathematical formulations provide insight into the inner workings of the VQ-CPC architecture, highlighting the distinct roles of the aggregator network, codebook vectors, and encoder in learning discrete representations. By leveraging self-supervision, the proposed approach can effectively recognize human activities from wearables-based data without relying on manual annotations.